Today we're going to look at section 2.1a, Relations and Functions. Our objectives are to define relations, domain, range, and functions, to be able to determine if a relation or graph represents a function, to find the domain and range from a relation or graph, and to evaluate a function when using function notation. So what is a relation? Well, it's just a mapping or pairing of input values with output values. So we substitute something in, and we should get some sort of value as an output when we do that. We have a domain, and that's just our input values. And our input values are usually our x values. Okay, so our x values. And likewise, our range are our output values, which are typically our y values. Okay, so when we have this pairing of x values and y values, we call that a relation. So let's look at 3 ways that we represent a relation in class. One is by looking at ordered pairs, the way you're probably most used to seeing x's and y's. So let's see, for example, I have the ordered pair 5, 1, how about 2, negative 3, 7, 0, and let's do 9, 1. Okay, I'm just going to put brackets around it to show that they are all together, and that makes my relation. So if I ask you from this relation what my domain and range would be, well, my domain is my input values, or are my input values, or my x values. So I look to see all my x values. Now I don't have to technically write them in numeric order, but I'm just going to kind of write them as I see them. I know I have a 5, a 2, a 7, and a 9. And if you want to put them in order, you're more than welcome to. And if I look at the range, I have a 1, a negative 3, a 0, and I have a 1 again, but since I've already listed it, we don't list it twice. So this is my input values and my output values. So we're used to seeing it as an ordered pair. When I look at it as an ordered pair, I can tell which input value goes with which output value. When you look at it in the domain and range, you can't tell. Another way we talk about it is with a table or mapping diagram, and that is done very similar, but it's kind of looks a little different than you might have seen. So we have 3, let's say, negative 2, negative 7. Okay. Let's pretend like these are my x values, or my input. Okay. And then over here we're going to make our y values, or my output. Okay. And let's say I have 10, negative, let's say 5, negative 6, and say negative, I don't know, 9. All right, so these are my input, these are my output. So what I need to do is show you as a map which one goes to which. So let's say 3 maps to negative 6, and say 2 maps to 10 and negative 5. And let's pretend negative 7 maps to negative 9. If I asked what the domain and range would be, well, the domain are just my x values, or my input, and my range are my y values, or my output. Okay. Now, this kind of mapping could go straight to ordered pairs. Now, it doesn't look like ordered pairs, but if I did write this as an ordered pair, 3, my input goes with my output of negative 6, negative 2 has an input of 10, or an output of 10, and an output of negative 5. And my last one, negative 7, has an output of negative 9. So these represent the same information. Our last way that we're going to deal in class with a relation is by graphing our points, our input and output. So we might have an input of 1 and an output of 3. Okay, so that would be my input of 1, my output of 3. I could have negative 7, negative 6. So I'd have negative 7, negative 6. I could have 10, negative 2. So my input would be 10, my output would be negative 2. I could even have 10, 5, where 10 stays, and then I have 5. These are all different ways to show input and output values. So what if I don't give you just random points? What if I ask for domain and range, but I give you a full graph where it's continuous? So there's an infinite number of points. This can be a little bit more difficult. So I'm going to go through a couple of ways that hopefully make this a little bit easier to find. I need to figure out my input values, my x. So what I want to do is think about what x values are attained in here. And I'm going to do a shaded region, and I think that might help you out a little bit. So if I think about where this graph goes, If I want to shade all the places the graph is, okay, so if I think about here, this is the lowest my graph goes. Okay, this right here is the lowest the graph goes. Okay, the furthest right my graph goes would be right here. So that kind of boxes off where my graph is. My graph doesn't go anywhere over on this side, and it never goes further down here, but it does get trapped in here. So this kind of gives me my boundaries for my domain and my range, my input and output. Input are the x values. So if I look on the x-axis, the furthest right I go is right here at -9. Okay, and the furthest left I go, well, this arrow keeps going, goes on forever. It's going to go all the way to -infinity. So my x values is a range. So how do I show all the values from 9 all the way down to -infinity? Well, we can use an inequality. My x values are less than or equal to +9. My range are my y's, up and down. The lowest my graph goes is right here at -4. The highest my graph goes, well, if I keep going, this arrow goes up forever, is all the way up here to +infinity. So how do I show the y values that go from -4 to +infinity? Well, that would be all the y values that are greater than or equal to -4. And that's how we do our domain and range when we have a graph. It's going to be some sort of inequality or range of values. So let's look at another example. This one is more of a closed off region. So let me do the same sort of shading that I did with the yellow on the last problem. If I look at my graph, the furthest left it goes is right here. Okay. Okay, my graph doesn't go any further left than right here. The furthest right it goes is right here. The furthest any point on this graph goes is all the way over here to the right. So that would be from 1, 2, 3, 4, -5. Let me switch the color for you. From -5 all the way to +7. Those are my x values. My graph never gets less than -5, never gets greater than +7. So my x's are stuck in between that, kind of like an and inequality, compound inequality. So I'm going to go from -5 less than or equal to x less than or equal to 7. The reason I put the equal to sign is because my graph actually hits the value at -5 and at 7 right here. So let's look at the y values. The lowest my graph gets is right here at this value at -9, and the highest it gets is right here at +7. So it's 7 and -9. And these are my y values. So I'm going to show that range as -9 is less than or equal to y, be careful that you put a y, less than or equal to 7. And that's how we do our domain and range from a closed graph. So now we're going to talk about functions. So we deal with relations, but now in Algebra 2, we deal a lot with functions. And a function is just a relation that has each input goes to exactly one output. One of the easiest ways to think about that is to go back to our mapping kind of diagram here, like we had on the other page. So for example, let's just have I have 5, 4, 3. Over here, if I have 6, 7, 8. As long as this input goes to only one output, this input goes to one output, this input goes to one output, that is considered a function. Each input goes to exactly one output. Now, what if I add an extra arrow? Now my input of 5 matches up with 2 outputs. That means it's not a function. So there's lots of different analogies that I've heard people kind of give for this, but I like to use kind of just think of a machine. A function is like a well-oiled machine. If I put something into my machine, I should always get the same output, the same product. So I know that if I put into my machine of 4, I will always get an 8. Okay, that's a good machine. I know that I can predict it. If I put in a 3, I know I'm always going to get a 7. But if I put in a 5, sometimes my machine spits out a 6, sometimes it spits out a 7. And since I can't predict that, that's no good, so it's not a function. Okay, it's not a well-functioning machine. That's kind of a way I like to think about it. So we're going to kind of go through some examples of figuring out if it's a function or not. So here's a couple relations. Here's our ordered pairs. And I want you to be able to tell me yes or no if it's a function. So what you want to do is look at our input values only, which are our x values. So what I notice is that I have a 3, a 4, a -2, and a 3. Now once I see this repeat, then I get kind of concerned. I have a 3 and I know it goes to a 5. But that 3 over here also goes to a 1. Because it goes to two different outputs, this is not a function. If I look at example 2, let me look at the inputs again. I have 5, 4, -2, and 0. None of my inputs repeat, so I don't have to worry about them going to two different outputs because every ordered pair is going to have exactly one input and one output. Since there's no repeats, I don't have to worry about it. This would be a function. All right, so let's look at our mapping. This might be a little bit easier to tell. Let's look. Input goes to 1, input goes to 1, input goes to 1, input goes to 1. So this would be a function. Okay. If I look over here, I have a problem. My problem lies right here with this 7. This 7 goes to a -2 and to an 8 because it has two different outputs. This is not a function. Now I want to stress to you that we only care about the input going to two different outputs. If you look at this example, this output comes from two different inputs, and I don't care. That's an okay machine because I know if I put in a -1, I'm always going to get a 5. If I put in a 6, I always get a 5. I can always predict what my answer at the end is going to be. But sometimes I'm going to give you a graph. So how can we determine if a graph is a function? Well, you might remember this from algebra. It has to pass the vertical line test. So again, a relation is a function if and only if no vertical line intersects the graph of the relation at more than one point. So let's go through some examples of that. So if I have my vertical line, so I have this vertical line, as long as wherever I put it, it only hits my graph at one exact point, that is considered a function. So if I put it here, you can see that it hits the graph right there. If I slide, no matter where I slide it, this red line intersects the black curve at exactly one point every single time, which means that my input, my x, goes to exactly one output, the black line. So this first one would be a function. Let's look at my second example. Now when I slide this across, you're going to see hopefully right away that my red line hits my graph more than one place. So this would not be a function. And the reason that is because if I go to this input of -3, how do I know which answer to give? Do I give an answer of 5? Do I give an answer of -4? So because I don't know what answer to give, that's why it's not a function. So the last thing we're going to talk about is function notation. We're used to seeing problems that look like this. Y equals 2x plus 1. This is our xy notation. We typically, once you get into higher math, we don't use xy notation as much. We use what we call function notation. And function notation for this example would look like this. The function in terms of x is equal to 2x plus 1. It's not much different. We replace y with f of x. And it doesn't have to be f. We typically use f. Sometimes we use g. Sometimes we use h. It's just the name of the function. So this would be function f. Okay, and because it's a function, I know that every input should give me exactly one output. And this x tells me what my input values are. I'm inputting x, and then I'm going to get an output for my function. So let's go through a couple examples. If g of x, so my g function, is equal to x squared minus 6, find g of 4. So what this is asking me to do is this 4 is my input. So they're asking me to take my input and put it into my machine, my function. So I know if I take my machine, the g machine, and input a 4, what that means is I'm going to go to my function, and anywhere I see an x, I'm going to substitute in a 4. So this is going to be 16 minus 6, which gives me 10. So what this means is g of 4 equals 10. If I input a 4, my output's 10. This is the same thing as saying that the point 4, 10 lies on this graph, my input and output. Let's look at the second example. Okay, if h of x, so my h function, equals 4x minus x cubed, find h of -3. So this is saying go to your h function. I'm going to input again, this is my input, a negative 3 into my rule, or my little function machine. So I'm going to have 4x, oops, let's actually substitute it in for us right there. So I'm going to have 4, I'm going to input it right away, negative 3 minus negative 3 cubed. Always use parentheses when using your substitution. Okay, 4 times negative 3 is negative 12, minus, I'm going to do my exponent first, negative 3 cubed is a negative 27. So I'm going to get negative 12 plus 27. Okay, and when I add these, I should get 15, which tells me that if I take my h function and I input a negative 3, I'm going to get an output of 15, which, another way of thinking about that, the point negative 3, 15 would lie on this graph. So we've looked at section 2.1, relations and functions. Hopefully you have a better idea of how to define relations, domain, function, and range. You're able to determine if a relation or graph represents a function, to find the domain and range from a relation or graph, and to be able to evaluate a function when using function notation.